Morning, everyone. I'm waiting for my iPad to start up so I can get my notes set up to take them. Anybody have any questions? Feel free to ask. We still got about another minute before class starts, but there's not very many of you in here anyway, so I gotta be careful. Great, good. There as well. Just wait for everybody to come in. iPad's on now. No questions? Feel free to type them in the chat. I've got that open as well. Letting the person in. Who else is coming in? I got everybody else there. That's good. Can all y'all hear me? Anybody? If you can't, of course, just type. I know you won't hear that, but probably you're seeing my lips moving and you're thinking, "Oh, I better let them know they can't hear me." So please type that in if that's what is happening. It does not appear to be. Hopefully. Okay, looks like we're ready to roll now. Mariana's still having a difficult time getting in. Not sure what's going on with them. Uh, Looks like she got in. Okay, good deal. All right, I did take the roll already, so I've got that. Again, I asked, does anyone have any questions about material in general? I am shooting for it. I'm still working this out with your lab instructor, but I was shooting for this coming week, not today and tomorrow, obviously, but next week. I think your lab's on Thursday night after class. If that's the case, that's what I was shooting for the first face-to-face test. And the first online test should be turned in by then. I've already made the online test and practice test one available. The actual online test or the actual face-to-face test, I will have a separate well, I might have a separate practice test for that. But if it turns out to just be chapters 1 and 2, which I think it will, there's no reason to do a separate face-to-face test for the or a separate practice test for the face-to-face test. So just be prepared that during lab time on Thursday, you may actually have a face-to-face exam. Look in Canvas and you'll see the equation sheet that you're allowed to use. You might want to go ahead and print that out, and you're going to be able to use that every test this semester. And you should really be starting to use it for your practice tests and your homework, so you always have that available. That gives you insight into what equations you might want to commit to memory as opposed to just using the ones on the spreadsheet. I mean, on the equation sheet. Obviously, there are some equations that the author offers that aren't numbered. Those are not ones that he ever really means you to just blindly use without deriving yourself. So if you see an equation that's worthwhile memorizing, but you see that it's not actually numbered in the book, that's probably an indicator that you really shouldn't be wasting your time memorizing it. But it's not bad to have it so that if you ever work it out and have to work a problem like that, you can derive the same result and you'll know what the result's supposed to be. So hopefully that'll be helpful to you. I just saw another person come in, so checking that now. All right. So, uh, yeah, I was just saying something was giving you a hard time logging in, Mariana. I was just pointing that out. Didn't know what was going on. I could tell it was just taking a long time for you to join. So I did say your name, but I didn't mean anything like I was asking you a question or anything. All right. Okay, so this today, since we finished chapter 18 last time, and you can find plenty of practice uh, problems to work with the ideal gas law, problems to work with the van der Waals equation, even the Clausius equation of state. Those are all things you can find examples of, both in the book as well as on my YouTube channel. But we're actually going in now into chapter 19, which will be heat and the first law of thermodynamics. And this chapter is actually one that takes a little bit of time. I think I might have slated in the original syllabus, I might have slated it to only take 1 day, but it's definitely one of the ones that should take possibly 2 days. I'm actually going to look at the syllabus right now. And also I'm going to look at helpful documents and links and see if I have the equation sheet. Yeah. So in helpful documents and links, there's something that says pH, or excuse me, it says 242 PHYSICS, chapter 17 to 31. That is, and it's a PDF document. That is your equation sheet. So make sure you do that. Make sure you download that and have a copy of it. Uh, your practice test is open and has been for some time, and your online test is open and has been for some time. I'm actually having it, just in case you guys didn't notice, it was actually it's due June 3rd. So that means you're actually supposed to have it done by midnight on Monday morning. I'm leaving that for right now, but I might actually move it to the 5th, which would be Wednesday night. That all depends. I don't want it due until the day the actual, or day before the actual test is due, the face-to-face test. So that's what I'm shooting for. All right, got another student. Put them on the roll. So keep that in mind. Got the student now. Cool. And the equation sheet is there. Uh, I'll let you know when I do decide to, if I decide to change the due date on the first face-to-face, or excuse me, first online test. I'll let you know. I will speak with Ms. Raskovic tonight and nail down to see whether or not we can do the test on Thursday, and I'll let you know sometime this weekend. But just be prepared, start planning for it, and notice if you're preparing for the online test 1, which covers chapters 1 and 2, you're already doing what's necessary to prepare for the face-to-face test. It's probably going to be on the same 2 chapters. In principle, I could add a chapter 3, but I'm okay with doing chapters 1 and 2 for your first test. All right. So I'm looking this now. That looks good. Got that. Okay. So what I want to start off with is I would like to start off with covering, darn, how'd I get there? All of a sudden I just jumped to chapter 3 and I was on chapter 19 not 2 seconds ago, and it just jumped back for no reason. So yes, chapter 3 is heat and the first law of thermodynamics. The sections we cover are heat as energy transfer. Section 19.2 is internal energy. Section 19.3 is specific heat. 19.4 calorimetry and solving problems. 19.5 is latent heat. 19.6 is the first law of thermodynamics. 19.7 is thermodynamic processes and the first law. 19.8 is molar specific heats for gases and the equipartition of energy. 19.9 is adiabatic expansion of a gas. and 1910 is heat transfer, conduction, convection, radiation. So we'll actually cover all these sections this time. That's very important. All of those sections are important. And in fact, we normally at TCC have skipped chapter 20, but that is the second law of thermodynamics. And I just can't see a way in which I teach a calculus-based physics class that covers thermo and not cover the second law of thermodynamics. So we'll at least be doing a quick and dirty version of chapter 2 so that you will understand the various versions of the second law of thermodynamics and how to apply them. So what I want to start off with is regarding last time, we actually worked on not only did we use the kinetic theory to derive a relationship for the average kinetic energy, translational kinetic energy of the molecules in an ideal gas, and we found that the average kinetic energy, translational kinetic energy again, so the average kinetic, or excuse me, the average translational kinetic energy of an ideal gas is equal to 1/2 times the mass of the atom or molecule times the square of the root mean square velocity. And that's equal to 3/2 kT. Okay, so that's what we derived. Then we found that Maxwell worked out the Maxwell distribution, which is 4 pi n times m over 2 pi kT to the 3/2 power v squared e to the -1/2 mv squared over kT. That is the Maxwell-Boltzmann or just Maxwell distribution. And I showed you how you could take a derivative of that and set it equal to 0, and that get us the most probable speed because it's the graph of f of v, and the maxima of that is what we call the peak velocity. And what we mean by that is the velocity that the molecule has when it's at the peak of the curve. It's not the highest velocity. That's not what peak is meaning there. But we were able to do that. We had already found what the root mean square velocity was, and remember the root mean square velocity would be the average of the square of the velocity and then take the square root of it. We had worked out that to be 3 kT over m, square root of 3 kT over m, and we had done that with the kinetic theory. And you can, in principle, do that with the Maxwell distribution. All you have to do is integrate from 0 to infinity f of v times v squared dv, and then divide that by n, and that'll give you the average velocity squared. And then, of course, you have to take square root of that, and that would give you the root mean square. You can also calculate the average velocity. That was the one I started for you and told you about using integration by parts. So I still recommend you do that. I will let you know a little hint. When you go to calculate the average velocity, what you have to do is, and this is a general truth for statistics in general, if you have a probability function, normally that probability function has to be multiplied by dv, and then you have to integrate over it. If you want to know the average velocity, you have to multiply the function, that f of v, you have to multiply that by v, and then the v times f of v dv, you integrate that from 0 to infinity, and that would give you the average velocity. If you wanted the average of the square of the velocity, then you'd actually have to take the integral of f of v dv, but you also have to multiply f of v by v squared instead of v. Okay, you could also calculate the average velocity cubed, in which case you'd say the integral from 0 to infinity of v cubed f of v dv. But in that case, notice the f of v already has a v squared in it. So even when you calculate the average velocity, you're going to have to compute an integral of basically a bunch of stuff times v cubed e to the -1/2 mv squared over kt dv. When you go to integrate that, you use integration by parts. And the way that I think is most beneficial and easiest for you is if you take the v cubed and make it v times v squared, because in the process of doing integration by parts, actually, let me just write that, because I think it seems crystal clear when I'm explaining it, and it might seem kind of clear to you when I'm saying it, but without the symbols and stuff, it might not make much sense. So let me go ahead and just do that. So I'm going to share my screen again. There it is with my iPad. share my screen with my iPad. And if you'll notice, I'm looking up. So notice I told you that the f of v is 4 pi n times parenthesis m over 2 pi kt, close parenthesis, raised to the 2 halves, or to the 3 halves power. Notice there is part here where I left off a 3 halves. So I just wanted to refresh my memory on that. So I am right. That means what we're doing, if I want to calculate the average velocity, that's going to be the integral from 0 to infinity of v times f of v dv, and then you got to divide it by n. That's also equal to the integral from 0 to infinity of v times 4 pi n m over 2 pi kt to the 3 halves power times v squared e to the negative 1 half m v squared over kt dv, and of course all that will be divided by n, which at this point you can go ahead and do that to calculate those, or to cancel those out. But notice right here we have a v and a v squared, so this also is equal to, let's write 4 pi m over 2 pi kt to the 3 halves, integral from 0 to infinity of v cubed e to the negative mv squared, negative 1 half. Let's go ahead and do it 1 half here. Put the negative there and the kt here. dv. So that's the integral you got to do. The rule, you're probably familiar with this form. The integral of u dv equals, and this is a v, equals uv minus the integral of v du. Well, this is problematic because we often use the letter u for substitutions in integrals, and the letter v is already being used in our integral. So you might want to choose to use a different form. For instance, you could say the integral of sigma d phi equals sigma phi minus the integral of phi d sigma. That might be a better way of doing it. And the trick is this quantity should be easy to integrate. And this quantity should be easy to differentiate. So what I'm telling you guys is, if you make you should make, the way I have it written here is going to be d phi. You should make d phi equal to v e to the negative 1 half m v squared over kt dv, and you should then call sigma should just be equal to v squared, because what's going to happen is the sigma is just going to go on the right hand side of the equals right there, and the phi is going to go right there, and that comes from integrating d phi. Notice that since I have that v out in front in d phi, I can actually make the substitution. Hey, let's let negative 1 half mv squared over kt equal u, and then du would be basically negative mv over kt and we already got the V there, so I just have to multiply by KT over M and then multiply by M over KT, and that would give me basically the du that I needed. And also, that sigma is going to be what's integrated, and then the d sigma is the derivative of, well, let me show you in this case. So that means d sigma would equal 2v dv. So by doing it this way, you've reduced the variable v, which was a power of 3 being multiplied by e to the negative 1/2 mv squared over kt. By doing this, you've now reduced it to just plain 2v times e to the negative v over kt. So you can do the integration by parts a second time, and that time you automatically just get the du all by itself. Or actually, you don't even have to do an integration by parts. You can just do, since you have a v out in front and an e to the negative 1/2 mv squared over kt, you can just do a simple u substitution. So hopefully that'll help you guys. If you haven't started it, I'm afraid you might not get as much out of that explanation, but you can always go back to this video and look at it again when you actually start to try to do that. So definitely try to do that. I will tell you, this is the other part I was trying to show you. So for instance, if you wanted the square of the velocity's average, then that would be the integral from 0 to infinity of v squared f of v dv over n, which equals integral from 0 to infinity of 4 pi n m over 2 pi kt to the 3/2 times now I have a v squared, and I already had a v squared, so this would be v to the 4th e to the negative 1/2 m v squared over kt dv, and all that would be divided by n. So that's the actual average of the square of the velocity, and then of course you take the square root of that to get vrms. So vrms equals the square root of v squared bar. Okay, any questions on that? All right, how about any questions you might have on homeworks you've tried to do already, that kind of thing? Anybody have any of those? All right, it looks like we're okay on that one. So I'm gonna go ahead and swipe along. So what I want to introduce you to now is heat as energy transfer. So your book opens up with a chapter opening question, like I've told you several times before, at least twice before. So always answer that, try to get an answer, try to make sense of it. Don't be afraid of making a false hypothesis. That's just an opportunity to learn. But after that, it goes on to heat as energy transfer. And I'll tell you that historically, we initially, our scientists in general, initially thought of heat as an actual liquid. They called it the caloric, okay? So the caloric was thought to be essentially like a liquid. And if you, for instance, put a hot object in contact with a cold object, let's say you took a chunk of aluminum and you had it laying in the fire for a couple hours, and then you pick it up and put it up against a similar block of aluminum that had been laying on the table in the kitchen or something. Okay, what they pictured was some kind of fluid flowing from the hot liquid into the cold liquid. Okay, and they called it caloric, and they pictured heat as the transfer of that caloric from one object to another. Okay, now we've since gotten rid of the idea of caloric, but we still use the calorie, which was based on that. Okay, so it's a unit of energy, and the calorie is actually defined to be the amount of energy required to raise 1 gram of water by 1 degree Celsius. Okay, specifically, the calorie was defined to be the energy required to raise 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. So they even narrowed it down to specifically at what temperature. So that was defined to be the calorie. And then the kilocalorie, which is also written as cal, was also written as capital calorie, CALORIE, but in this case, the C was capitalized. And that's also what we call our dietetic calorie. So, for instance, if you go to eat, let's say, a Rice Krispie square that has 280 calories, that really has 280 kilocalories. Okay. But even though the fluid idea didn't pan out, we still not only use the calorie, we still picture heat flowing from the hot object to the cold object. And that's the direction it has to go. That turns out to be one version of the second law of thermodynamics is spontaneously heat flows from a hot object to a cold object. That's one of the versions of the second law of thermodynamics. What I need you to understand is that is what heat is. It's the actual amount of energy being transferred from one object to a different object as a result of a difference in temperature. So that's specifically what heat is. Anybody have any questions on that? Now I'm going to write down some stuff. I'll read it off first to you just so you'll have it, and then I'll write it down. But basically, the calorie is defined as the amount of heat necessary to raise the temperature of 1 gram of water by 1 Celsius degree. To be precise, the particular temperature range from 14.5 degrees Celsius to 15.5 degrees Celsius is specified because the heat required is slightly different at different temperatures. Oh, got another student. Okay. So just keep that in mind. I just had a student log in. Ah, Jonathan, you just logged in, right?
Yes,
Okay. I didn't have you on my roll. Did you just switch to the class, or are you from one of my other classes?
I switched to the class.
Okay, that's cool. Just making sure I didn't have you on my roll, so I was kind of stressed out. I'm going to write your name down here just so I remember it. I'm not going to say it out loud because this is going on the internet. I will let you know in case since you just switched. If you don't wish your name to accidentally pop up on my YouTube channel, you might want to put in basically your first initial of your first name, your first initial of your last name, and then follow it by the last 3 digits of your student ID, your IMPL ID. If you do that, then it's sort of, anonymous basically. But I'm going to write your name down here so I'll know it and have it on the roll sheet and have you listed as the day you first started.
Wait, and
Yes, someone said something. Was that you again, Jonathan?
you said and have, huh?
Oh, I'm sorry. I didn't say anything. It might be some noise that you're hearing. I just recorded your name, and today is your first day of attendance. I don't take off for attendance or anything like that, though.
Okay.
All right, so we got that going. And as I was saying, the calorie is defined to be the energy required to raise 1 gram of water by 1 degree Celsius from 14.5 degrees to 15.5 degrees Celsius. And then the kcal, also the kilocalorie, also the capital C calorie, is the heat needed to raise the temperature of 1 kilogram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. So let me go back to sharing my screen. And what we get here is 1 calorie. And of course, we want to make sure we put down the details here. 1 calorie is defined to be the heat required to change 1 gram of water at.
I don't think the iPad shared.
It didn't share. Anybody seeing it? Anyone not seeing it? Let's see here. It says it's showing on here.
I can still see.
I see it.
Okay, what does anybody know how he might have hit something or he or she might have hit something?
Oh, I got it. I got it.
Okay, cool. Usually my students know way more about that stuff. That's why I defer to them. So to change 1 gram of water at 14.5 degrees Celsius to 15.5 degrees Celsius, 1 kcal is also equal to 1 kilocalorie. But it's also equal to, notice the difference here. And that's defined to be the heat required to change 1 kilogram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. And in fact, there's another unit that you might be familiar with, and it's called the British Thermal Unit. And 1 BTU, British Thermal Unit, is equal to 0.252 calories, actually kcalories, and it equals 1056 joules, which we haven't defined yet, but you've had joules before in your conservation of energy and those chapters. Okay. And also I'll mention that there is a quantity called therm. So 1 therm is equal to 100,000 BTU. Okay. Now I will tell you that the BTU is defined to be the heat needed to raise the temperature of 1 pound of water by 1 Fahrenheit degree. So 1 BTU is defined to be the heat required to change, or actually to, I don't have a specification of what temperature was used, and it might not have been a temperature that was used. It sort of has to be, but since your author didn't give it to me, I'm going to ignore it and just say heat required to raise 1 pound of water. Oops. By 1 Celsius to, or excuse me, 1 Fahrenheit degree. Okay. So that should get you some understanding that clearly they really are talking about heat as something that just, can raise, for instance, the temperature of water, and all the units that you might be planning on using are actually based in that reality. So let me open up with a mechanical equivalent of heat. So it turns out that these guys by the name of Joule, James Prescott Joule, we call them Joule. I do know that there is a beer in Great Britain called Joules, and that's their family. Okay. So I'm not sure if they've always been called Joules, or if it's just the beer that's called Joules, or if it's the family saying, hey, our name's supposed to be Joules. I don't know. But the main thing is you get an idea from that history that in Great Britain, James Prescott Joule, or Joule, was a fairly, famous businessman that had started businesses. They made money by studying cannons and stuff like that, but they also brewed beer, among other things. So they really were trying to work out basically what the laws of thermodynamics were. And what they did is they had a hunch that we could probably relate this joule, which you guys learned as a mechanical energy term, that should be related to the heat listed by a calorie. So they tried to make an experiment where they could convert from, let's say, from one to the other. In other words, can you take mechanical energy and convert that to heat? And can you take heat and convert that to mechanical energy? And that's what the mechanical equivalent of heat is. And that was an experiment conducted by James Prescott Joule in the 1800s. So James Prescott Joule, and your book was kind enough to give us their lifespan, which was from 1818 to 1889, which happens to be the year that Huron went down by Nags Head Pier and Nags Head. Okay, so somewhere in that time period, he did the mechanical equivalent of heat. And if you've had physics before or chemistry before, you've probably thought of this result, specifically 4.186 joules is equal to 1 calorie, or 4.186 kilojoules is equal to 1 kilocalorie, which equals 1 calorie. Okay, you probably thought of that as just a conversion factor, and it is a conversion factor, but it's so much more than that on a physical level and on a conceptual level. It was a huge paradigm shift. They thought energy, like I said, was one thing, mechanical energy was one thing, but the caloric, which they originally thought, like I said, was a fluid, that was something entirely different. By writing this quote unquote conversion factor, you're saying, hey, these distinctly different physical concepts are actually two sides of the same coin. So it's a really big deal. Now, the way it was done is you could imagine if someone made a little prop like this, and they put a little propeller, basically, that's what I mean by prop. So you have a propeller connected to a little propeller shaft, and that little propeller shaft would sit in a container of water, like a beaker, say, and on that propeller shaft, which was held by, some kind of bearings and stuff like that, so it would stay upright, but on that was a spool around which string could be wrapped, and then there was a pulley, and you could hang a mass M from it, and you could allow the mass M to drop through a height H. Okay, and you could put a thermometer in here like this, and basically what would happen is you let that mass fall, and that mass would cause the propeller to spin. The propeller would cause the water to agitate. Basically, it's going to cause the molecules in the atom to somewhat try to go in circles, but the main thing is, in principle, it will ultimately lead to the net kinetic energy of translation in the motion of the molecules in the liquid. They're actually going to increase on average. Now, when you increase just a few of them from the propeller pushing the molecules or atoms around, that is not a temperature increase. But what's going to happen is those atoms and molecules are going to be moving quite a bit faster than the other ones, and then they're going to collide bunches of times with all the other atoms and molecules until the net effect is that the net average kinetic linear, or excuse me, I should say the net average translational kinetic energy of all the atoms or molecules, depending on what you're working on, will be larger. And to do that, what they realize is the mechanical energy would be M times G times H. And then they realize that the heat energy would be M times the specific heat of water times delta T. This quantity is called the specific heat. Okay. And you can see that the mass doesn't matter too much because it cancels out on both sides. But the main thing is you can see that this part would be measured in joules, and this part would be measured in calories. And from that, they got 4.186 joules is equal to 1 calorie. Okay, so that was a really, really big deal. And in so doing, what we've discovered is that heat, which is energy in motion from moving from a hot body to a cold body, is equal to Q, which equals MC delta T. Okay, so that's the symbol we're going to use for heat, is Q. And that's a formula that we can use for the heat required to change the temperature of a mass M of the substance that has a specific heat C by an amount delta T. So that's a lot of good new information that we can use. And in fact, that's going to be the case for all of them. I hope you can see that it makes some sense that the amount of heat you have to add, let's say you have a big vat of water or a big vat of I don't know, mayonnaise, anything, right? Any kind of container whose temperature is fixed and you have a mass associated with it, and you want to change the temperature of it. Well, it should seem reasonable that if you want to change the temperature by 1 Celsius degree, it would be about 1,000 times harder to change 1 gram of that substance. To change 1 gram of that substance by 1 Celsius degree, it'd be about 1,000 times harder if it was a kilogram. So that tells you Q should be proportional to M, which is what the formula says. Also, if you're changing it 1 degree Celsius, that takes a certain amount of heat. But if you change it by 2 degrees Celsius, it stands to reason that probably that's going to take twice as much heat. If you change it by 3 degrees Celsius, that's probably going to take 3 times as much heat. So that's why we've got Q proportional to delta T as well. And then finally, what we decided to do was we absorbed any possible constants of proportionality that we used into the constant that we use for the particular material. So the particular material will be represented by its specific heat, which is given the symbol C, and that is a lowercase c. Okay. Can anybody look at this equation that I have written down, and knowing that heat is measured in either in joules or in calories, can anybody tell me what the units of C should be?
Joule over kilogram Kelvin.
That's exactly one version. So yes, I would write the specific heat C is joule per kilogram. And it actually doesn't matter, but I'm going to write Celsius degrees. And remember, the Celsius degree means you've done a subtraction in Celsiuses. Whereas if I just wrote Kelvin down there, it'd be the exact same number, but Kelvin doesn't have a degree on it. So this doesn't remind you that it has to be a difference in degrees that's multiplied by it. Another unit, though, would also be the calorie per gram Celsius degree. So both of those are completely acceptable. Good answer, by the way. So that is something important. You always want to think about the units whenever we give you new equations and stuff like that. So let's look at an example. Your book does one that's kind of neat. So let's say we go, I think I think Kentucky Fried Chicken stopped selling this thing, but at one point, Kentucky Fried Chicken had the most unhealthy thing in the world. It was something like 1,500 calories in one of these, whatever it was. I want to say it was some kind of chicken sandwich or something, but it had a lot of bad stuff on it. Bad in the sense of a lot of calories. So let's imagine. Actually, let me. I don't have enough room there, so I'm gonna. So I'll read this to you. So imagine you ate a really high calorie meal, but then plan to work off the energy by stair climbing. If you assume your mass is 70.0 kilogram and your body is about 20% efficient, how high would you need to climb? Okay, so you're trying to burn off all 1,500 calories, and you're doing so. I'll first do the calculation, but we're going to do so by climbing stairs. And we're going to assume that the work that goes into climbing stairs is basically the change in potential energy, which is obviously M times G times H. Okay. Then we'll adjust for the actual efficiency. So here's our solution. So we want 1,500 calories. Notice that's a capital C. So that is 1.500 times 10 to the 3 capital calories, which equals 1.500 times 10 to the 6 lowercase calories. Okay. Now we can take 1.500 lowercase calories and put that over 1 because we're getting ready to do a unit conversion. And what we're going to do is realize that 4.186 joules is equal to 1 lowercase calorie. And that'll give us the total amount of calories, but specifically in joules. So it's the energy equivalent of that meal that we ate. So I'm going to say 1.5 times 10 to the 6th, 1.5 e to the 6 times 4.186. That gives me 6.279 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6 joules. Okay. Now I need that. Let's call this E. We need this E to be equal to mgh. if we ignore efficiency? Okay, so if we do that, what we'll see is 6.279 times 10 to the 6 joules is equal to 70.0 kilograms times 9.80 meters per second every second times h. So h is going to give us 6.279 times 10 to the 6 divided by parenthesis 70 times 9.8 close parenthesis. That gives me 9,153 meters. Okay, so you can see that's quite a bit. Remember, it's only 5,280 feet in a mile, and a meter is 39 inches. So it's like 3 inches more than 3 feet. So this is well over 3 miles. In fact, it's very close to approaching 6 miles in height. So that's kind of a big deal, right? So this is on the order of 6 miles, but ignores our metabolic efficiency. Now, I will tell you efficiency which we often use symbols like this one, for instance, eta, is what you get divided by what you pay for. That's one way of thinking about it. So when we say eta equals 20%, that means 0.200 is equal to what you get divided by what you pay for. So if you want to be able to burn enough energy to get to this height of 9,153 meters, you actually are not going to have to go that far because your body's going to have to waste a ton of energy to get there. So you could say what I'm actually going to get is basically a energy of 6.279 times 10 to the 6 burn out, but I'm actually going to put in a lot more than that. So you might think to yourself, actually, I don't know if I want to do it this way. That's why I'm pausing here with the 0.20. What you get versus what you pay for. So what you pay for is the number of calories that you're ultimately going to burn. So that's the 9,100. Oops, not 9,000. That is the 6.279. Whoa. Times 10 to the 6 joules. And this will be what you pay for. So this is really going to be the total amount of energy that you're going to get out of it. I think that's right. Nope, that's not right. Yeah, that's a bad thought. Okay, let's think about it this way. I hadn't thought this through, so I'm obviously getting a little bit mixed up. So I want to make sure we are on the same page. So if we're thinking that the body's 20% efficient, that means if I put in, let's say, 100 calories, if my body actually burns 100 calories, only 20 of those calories can go to work. So if, let's write that out so we can help ourselves understand. If my body burns 100 calories, then only 20 calories can be used to do work, because 80% is wasted. Okay, so hopefully, I don't know why I put an I in there. Whoa, no. So now we can use that as an idea of what we're going to do. So if we want to do that, we're going to say, okay, I actually need to get a net of 627 or 6.27 times 10 to the 10 to the 6 calories or joules. So want to burn 6.279 times 10 to the 6 joules, but only 20% of those can be used. Oops. For M times G times H. So what that means is 0.2 times 6.279 e to the 6 is equal to 1.256 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6 joules will lift me. Therefore, 1.256 times 10 to the 6 joules is equal to 70.0 kilograms times 9.80 meters per second times H gives us H is equal to, now you can imagine that's just going to be 20% of the height, but we'll work it out either way. So I'm going to take this 1.256 times 10 to the 6. I'm going to divide that by parentheses 70 times 9.8, and that's going to give me 1,831 meters. So that's a lot more reasonable, and that's very, very doable. That's closer to literally a mile, but that's still a lot of climbing. So, so don't forget that. Anybody have any questions on that one? Now, you can go back and try to relate that efficiency, what you get divided by what you pay for that. But I hadn't even used that formula in well over, well, heck, I haven't even actually applied that in a couple of years. So I just wasn't ready to quickly throw it down in the appropriate fashion and hope that it got right. So I figured I'd draw back, think about it in a way that I understood and that I could easily explain. And that's what I did there by saying that only, 20% of the energy you burn is going to go to do useful work, i.e. lifting you up the mountain. So does anybody have any questions on that? Sorry about pausing a little bit for screwing up there, but
So why would it take less distance to burn all the calories if it's only 20% efficient? Wouldn't it
because
take
your
more
body,
to make up?
go ahead. Yeah.
Yeah, wouldn't it take more distance to make up for the 80% that you're wasting?
Normally that is the way you think of efficiency, but in terms of the human body, we take in, 3,000 calories a day, and some huge fraction of them goes to just keeping our body moving, living, that sort of stuff. So if you take in 3,000 calories, it's essentially impossible for you to use or to expel 3,000 calories of energy in doing work if that's all you've eaten. So the same way here, if you eat, 1,500 calories of food and then you go to try to work out, you're not going to be able to get that full 1,500 out. In fact, your body's only 20% efficient. So 80% of that 1,500 calories is going to be wasted in just, keeping your heart flowing, keeping your brain pumping, your brain working. I think they reported that your brain runs about 120 watts. So your brain, just by being a brain, requires 120 watts to just exist as a thinking brain. Then you got to think about, well, my heart's got to actually apply forces and pressures to push blood through the body. Of course, that all takes energy. I've also got to convert, glucose into ATP, and that's not 100% efficient. So yeah, all of that tells you that there's some amount of energy that's got to be wasted in you trying to climb a mountain. So the amount you can climb is never, quote unquote, the amount that you take in. So hopefully that helps explain it to you a little bit. Is that
Yeah, that makes sense.
okay? Yeah, but that is exactly what you're used to in terms of efficiency. If you say that a engine is 80% efficient instead of 20% efficient, you get even farther than you did under the 20% efficiency. But in this case, the efficiency is really a matter of how much energy we can free up to make our muscles move and stuff. So you can think about it that way. All right. Anything else? All right, so that was really our introduction to heat and the different units that we'll use. What I'm now going to introduce you to is something called internal energy. And we use a very specific symbol for it here. If I remember correctly, we're using just plain E. So your book says the sum total of all energy of all the molecules in an object is called its internal energy. Sometimes thermal energy is used to mean the same thing. We introduce the concept of internal energy now since it will help clarify ideas about heat. So the internal energy, E, trying to get a blue marker here, E is internal energy of an object. It is the sum total of all the energy. Oops, I did a EM of all the molecules in an object. Now, notice that means what we talked about before when we did the kinetic theory. We actually calculated the average translational kinetic energy of the molecules. That means molecules that are moving forward, backwards might represent the X direction, left, right might represent the Y direction, and up, down might represent the Z direction. If we just take into account that motion, then we're just getting the fraction of internal energy that's associated with temperature. And that's just plainly the molecules moving left, right, in, out, up, down. That doesn't talk about the molecules rotating this way or rotating this way. That doesn't talk about them vibrating like this or vibrating like that. That don't talk about them rotating this way. It also doesn't talk about potential energy between two atoms or molecules being very close to each other. That's not included in that temperature-related energy either. But the internal energy takes into account all of that. So the internal energy is all the kinetic energy of translation, all the kinetic energy of rotation, all the kinetic energy of vibration, so the individual atoms vibrating at the ends of the molecules. Also, all the potential energies. That is what the internal energy is. And you can, of course, use that in joules or calories, doesn't really matter, but both are valuable, okay? So if you try to distinguish between temperature, heat, and internal energy, one of the ways you can think about it is heat, remember, is the energy in motion or energy being transported. Heat is not something that an object has. Heat is something that can flow from one object to another, but you never say an object has such and such a heat in it. No, you say the object has internal energy in it. And then when some of that internal energy disappears as energy is flowing out of that object into another object, that's when that particular part of the internal energy became heat. Does that make sense? Anybody have any questions about that? So your book says things along the lines of using the kinetic theory, we can make a clear distinction between temperature, heat, and internal energy. Temperature in kelvins is a measure of the average kinetic energy of individual molecules, and specifically, remember, that's translational kinetic energy. Internal energy refers to the total energy of all the molecules within the object. Thus, two equal mass hot ingots of iron may have the same temperature, but two of them have twice as much internal energy as one does. Heat finally refers to a transfer of energy from one object to another because of a difference in temperature. So hopefully that helps you. You can read that, of course, in section 19 too. But what we're going to do now is we're going to work out the internal energy of an ideal gas. So let's calculate the internal energy of N moles of an ideal monatomic gas. Okay. The reason why we are focusing on monatomic is, remember, two parts of the kinetic energy I told you about was, for instance, if you imagined this guy right here might be a molecule, maybe this is a big atom on this end and a small atom on this end, then you have an energy not only associated with it moving left, right, in, out, and up, down, you have an energy associated with it rotating this way. That's not part of the translational kinetic energy, but it is part of the internal energy. Then you have another energy associated with it rotating this way. Okay, that's another part that's part of the internal energy, but not part of the energy that we associate with temperature, namely translational. There's also technically an energy associated with it rotating this way, but that's so minuscule we don't even care about it because atoms are, atoms and molecules are really, really small in diameter. So if it's rotating just about an axis right through the center, that's not very relevant. In principle, it could come up, but it just isn't an appreciable amount of energy. Now, in addition to that, you could also have energy associated with this atom vibrating and this atom vibrating. That's another type of energy that has to do with internal energy, but not that translational kinetic energy. But if you reduce yourself down to a monatomic molecule or atom, then you basically have a single dot, basically an infinitesimal sized molecule, which isn't really infinitesimal, but it's on the order of 10 to the negative 10th meter. So it's very small. So it takes nothing to rotate it this way, to rotate it this way, or to rotate it this way. None of that really matters. So really, you only have translational kinetic energy when you talk about monatomic atoms that are monatomic gases. So that's why we're doing that. So let's talk about this now. I'm going to say internal. Oops. Everything's stopping to work. Okay. Okay. So E internal remember when we treat an ideal gas, we assume it has N atoms or N molecules. So since this atom can't rotate about its axis in any appreciable energy sort of way, any of its axes, we only have translational motion. So the internal energy is going to be the number of atoms times the kinetic energy of each atom. And the kinetic energy of each atom, of course, is 1/2 mv squared bar, like that. But we also know that 1/2 mv squared bar is equal to 3/2 kT. So we can say that E internal equals 3/2 nkt for an ideal monatomic gas. And it has to be an ideal gas because that's what we did use to derive the 3/2 kT formula. Now, you could also use the fact that since K is equal to R over Avogadro's number, then you could say E internal is equal to 3/2 N times R over Avogadro's number times T. But then N divided by Na is the number of moles. So we could just write that as 3/2 nRT. So another form is E internal is equal to 3/2 N times R times T for an ideal, monatomic gas. Okay, so we've got two expressions we can use right now. As long as we deal with monatomic gases and ideal gases, then that should be fine. Your book takes some time to express the idea about diatomic gases and how they could rotate this way, or they could rotate this way, but they can also vibrate this way, that kind of stuff. That's important. You need to start understanding that, and we're going to get into it. And in fact, there's ways to generalize the internal energy and other energy formulas for those other types of gases. And that's ultimately what we're going to be able to do in this chapter. But now that we've done that, we've now completed the internal energy portion, and now we're going to go to specific heat and make use of that. So let's go to specific heat. Whoa. So specific heat is defined such that we have the equation Q is equal to MC delta T. And remember, that's also the same as MC times T final minus T initial, because delta always means final minus initial. So this is an important equation. We'll make use of it several times. But this really just gives us a heat in joules or calories, depending on what specific heat you use, what units you use. It gives us the heat required to raise the temperature, or the heat required that you remove from an object to lower its temperature. Notice if the T final is smaller, notice if T final is smaller than T initial, then you're actually cooling it down, which means you're taking heat away from it, and that gives you a negative Q value. That's something important to understand. So let me write that here. Q less than 0 implies heat is lost from the object. whereas Q greater than 0 implies heat is added to the object. And just to give you some idea, for instance, specific heats, let's say specific heat of aluminum, that's equal to 900 joules per kilogram Celsius degree, or it's also equal to 0.22 calories per gram Celsius degree, which is also equal to 0.22 kilocalories per kilogram Celsius degree. If we wanted to know, for instance, darn it, I hate it when it keeps doing that. If we wanted to know the specific heat of, let's say, copper, which is Cu, we know that one's going to be 390 joules per kilogram Celsius degree. And that, of course, is going to be 0.093 calories per gram Celsius degree. And you can see there's no reason to write a different number for kcal per kilogram, right? As some outliers, you might realize that the specific heat of alcohol is actually 2400 joules per kilogram Celsius degree, and that's equal to 0.58 calories per gram Celsius degree. And then the specific heat of water is equal to basically liquid water is 4,186. And in that case, it's joules per kilogram Celsius degree. And that's, of course, equal to a much nicer number. Dang it. 1.00 calories per gram Celsius degree. And this is at change my color, at 15.0 degrees Celsius. Okay. Ice, on the other hand, has an entirely different value. It has a value of 2100. So C ice is 2100 joules per kilogram Celsius degree, and C steam is equal to 2010 joules per kilogram Celsius degree. So that's actually not written very well. Just in case y'all refer back to that, I'm going to clean it up a little bit. Okay, and of course, this one's at 110 degrees Celsius, and this one is at -5 degrees Celsius. Okay, so that gives you some values of specific heat that might come in handy. The human body, for instance, is 3,470 joules per kilogram. Protein is 1,700 joules per kilogram. All that stuff, comes relevant when you start studying biology as well. So really, the heat depends on how big the specific heat is. And in fact, you can explain simple things. Let's stop for sharing this for a second. So, for instance, you might notice that the United States has a part of it up around Maine, for instance, that's about the same latitude as Great Britain. Yet Great Britain has temperatures, other than it has a lot of rain, it has temperatures very comparable to what we have here in the Tidewater area. And the reason why that's the case is Great Britain is this island, in the North Atlantic, basically, but it's surrounded by water, and the body of land is fairly small compared to the huge amount of water around it. And because of that, when the sun bears down in the middle of the summer on Great Britain, the land warms up rather quickly because land has a lower specific heat. Most land has lower specific heat than water, whereas the water temperature will lag behind. And you know this if you just been swimming at Virginia Beach or in the Outer Banks, even on June 20th, which is the summer solstice. Okay, even around that date, you might occasionally run into the ocean being as warm as 78 degrees or even 82 degrees, but the air temperature then is on the order of 100 degrees, right? So that's because of the cooling effect, or the, I should say, less extreme effect of water. So when it gets winter, and for instance, you're around 1220, which is roughly the winter solstice, the temperature can be quite cold. Let's say up in Maine, for instance, the temperature might be negative 20 degrees Celsius. Okay, that's really huge. Or actually, probably not negative 20. That probably wouldn't be very reasonable, but it does reach that in some really, really cold places. But let's say close to 0 Fahrenheit. If it's close to 0 Fahrenheit, you could probably still jump in the water. It's not necessarily going to be pleasant, but it might not be any cooler than 48 degrees, 45 degrees Fahrenheit. Again, it's a moderating effect that the water has on it. So water having a high specific heat actually causes land to be more moderate. If you talk about the middle of our country, it can actually feel quite warm during the summer, and that's because there's less water around to keep it cool. And of course, that means it's also less humid because there's not as much water around. Now, with global warming, basically what the premise of global warming is that greenhouse gases in particular have the potential to retain more heat within our atmosphere than otherwise would be retained, just because of the greenhouse effect. Now, if we didn't have a greenhouse effect, the average temperature on the surface of the Earth, I think we worked it out one time to be on the order of, I want to say it's like 12 Celsius or something like that, pretty low. So around 50 degrees Fahrenheit, somewhere around there. I think that's what it was. And in some places, that means the temperature would be 0 all the time, and that's extremely, extremely cold. But luckily, we have some, greenhouse effect that keeps it a little warmer than that. But what's happened now is we've exceeded even what we've had in the last tens of thousands of years. And because of that, the average temperature over the whole atmosphere is higher. That means the air can retain even more water dissolved in it, because basically water can absorb a certain amount of water based on what its temperature is. So for instance, if you sweeten your tea while it's still hot, like you just finished boiling the tea, and then you add a butt ton of sugar to make it sweet, you can do that because hot water can absorb a butt ton of salt, of sugar. Whereas if you cool the tea down and then try to add the same amount of sugar, the sugar's just not going to stay in. It's going to pool on the bottom and that sort of thing. Well, the same thing happens with our atmosphere. At higher temperatures, it can absorb more water. So now the air that might have been over Kentucky or Kansas or something like that has the likelihood of having more energy in it, specifically because it's higher temperature, and having more water in it, specifically because it's higher temperature. And therefore you get more severe storms and stuff like that because of the extra energy. But you also get more humid in areas where it wasn't humid before. Any questions on that? Okay, so those are some big concepts in general about how water can affect things. And there's even neat little ideas where you can actually understand why do you get a breeze in one direction during the day and another direction during the night. Well, during the day, for instance, it's normally the sun is hot, the air is hot, and the water is the cold thing. So the water is actually absorbing heat from the environment. So that looks like a low pressure zone. And the air, or excuse me, the ground adjacent to, in other words, the beach and the land, that sort of stuff, that's actually going to get hotter and actually tend to cool off by letting heat out into the atmosphere. So the land part will actually allow heat to flow out of it, that'll actually cause the air to lift over there, but sink over here. And this air lifting over the land causes a low pressure zone. So you'd end up having wind blowing from the water onto the land. That could be a possibility. You could also have the reverse if the actual heat was being given off by the water. So for instance, at nighttime, the air can get colder than the water, especially during the summers, in which case the heat actually emanates from the ocean and heats up the air above it. That causes the air above it to lift, and then that causes an offshore breeze. So that's a scenario in which you can understand particular breezes. Any questions on that? All right, so let's go ahead and take a break. It's 6:54. Let's go ahead and take a break till 7. And I'll be here if anybody has any questions, but you guys go ahead and take a break till 7. And I'm here if you need me. I get talking, I just forget that I should give y'all breaks. I apologize for that. Feel free to call me on it anytime. I won't take it as rude. Y'all definitely, you get a break. I mean, that's pretty normal.
When the water absorbs the heat from the air, why does that create low pressure?
When the water absorbs heat from the air, I don't know that it should. I was using a specific example. I'm not sure that it naturally does that. Let me think about it a little bit, but hot air in general, we know hot air rises because basically just about everything expands upon getting heated up. So if we allow the air to get hotter, it's going to be less dense and it's going to lift up. So, yeah, that should actually be it. So if water, what I said was an example that's sort of counter to the norm. So if you think about water as warmer at nighttime, then the water will be a higher temperature than the air above it. And from the second law of thermodynamics, that says heat will flow from the water to the air. If the heat flows from the water to the air, that's going to take the let's say wafer of air right above the ocean, and all of that's going to heat up. When that heats up, that's going to actually cause the air to expand. That air expanding means it's lower density, so it's going to lift. So what that does is actually leave a low pressure over the ocean, and then the offshore breeze will come in to fill it in, because any low pressure zone is going to have wind blowing towards it. In this case, it's going to blow from the land onto the water. So you should have an offshore breeze, meaning a breeze that comes from the shore during the night, as a norm in the summer. In the winter, it can be reversed, but as a norm in the summer, basically the warm water will release heat into the air, and the air will then expand, and that expanding air will lift. That leaves a low pressure right below it because it has less air there. And since it has less air there, and therefore it's low pressure, that means the wind is going to fall towards that low pressure, which is from the land onto the water. So I actually explained exactly the opposite of what you asked, because I was using a specific example, and that's why I didn't go into details as to what season it was, because I couldn't remember which way it would happen. But if you actually work through the heat of it, remember one thing that's false is heat doesn't rise. That's often something that we say in everyday life. I'll hear firefighters say that, and I know exactly what they mean, and they're not, stupid or anything. They're just, speaking the easy way to speak. Heat does not rise, though. Hot air does rise. But then again, so does, hot liquid silver. So if you actually got silver to the boiling point and then went further to the actual gaseous point, then the hotter silver gas would actually be lower density than the colder silver gas, so it would lift. So that's sort of what's going on here, is because the heat in the water, which is warmer than the night air during the summer, that heat can be delivered from the water to the air. Then a wafer of air sitting right on top of the water will actually get heated up. That will make it be less dense, so it'll spread out to a larger volume and it'll float up. And that leaves less air pressure there, and therefore it's the definition of a low pressure zone. So then air can blow towards it from every direction, but more specifically, you're used to breezes coming off the land at night and then breezes coming off the water at day. That's actually what we look for, at least on the Outer Banks. We look for water blowing or wind blowing onto the shore from the water for the clearest of water. That also makes it rougher, but it also makes it warmer. And it does tend to make it more clear. So if we have like a 2-week period where there's a light easterly wind blowing from the east, then the East Coast tends to get clearer water, at least after a couple days. I've actually been lucky enough to go scuba diving at like the 7.5 mile post, scuba diving or snorkeling, and have like 200 foot of visibility, even on the Outer Banks. It doesn't happen, but maybe once or twice a year, as far as my experience goes. But it does happen. It's really cool. Hopefully that helps. Sorry about the hemming and hawing in the other part though.
It's pretty cool because you just think of like the wind is just coming from the exchange back and forth night and day.
Exactly. Yeah, it's almost like a closed system all by itself. Then if you go look at the West Coast, they're really weird because the West Coast, the water's surprisingly cold. Here we have the Labrador current that comes obviously from Labrador in Canada, and goes down our east coast, but we also have the Gulf Stream that comes up from the Gulf and actually comes up along Florida, and then they sort of merge somewhere off the coast of Cape Hatteras. Uh, but if you're in the Labrador current, the water is a lot greener and not nearly as clear and quite a bit colder. Whereas if you're in the Gulf Stream, the water is bluer and warmer. Where when you go to the Pacific, you actually find that the water is pretty much always cold. It's not unreasonable to find fairly cold water temperatures, even in Southern California. Hawaii, for instance, often has, I mean, they have, since Hawaii has such great weather in terms of heat, they have warmer water, but it's still not as warm as you'd expect it to be, and that's because it's in the Pacific. All right, it's 7 o'clock, so I guess we'll go ahead and get started. So I'm going to look at another example here. Anybody have any questions before we get started? All right, so I'd like an example for you to get some understanding of how the specific heat affects the temperature change. So what we can do is imagine two identically massed objects and find out what the temperature change will be when we add a certain amount of heat to them. So in this case, we're using iron and water. So I'm going to say solution. And for the solutions, I need specific heat of iron, which is Fe. And hopefully that's one I know or I can look up. I don't see it. Silver, mercury, marble, lead. Oh, iron. There it is. Okay, so this is going to be 450. That's 450. Oh, that does not look like a good 50. 450 joules per kilogram Celsius degree, and specific heat of water in the same units is, of course, 4,186. In that case, it's kilojoules per kilogram, or excuse me, joules per kilogram Celsius degree. And what we're going to use is Q equals MC delta T, where Q is equal to, what did I say, 5,000 kilojoules? So I'll say 5.000 times 10 to the, that's 10 to the third kilojoules. So that should be 10 to the 6 joules. So first part, iron. Delta T, according to this equation, should be Q over MC. So this is going to be 5.000 times 10 to the 6 joules divided by 20. Oh, and I should have written that as well. M is equal to 20.0. Nope, it's 30. Sorry about that. 30.0 kilograms. So this is 30.0 kilograms times, for iron, it's 450 joules per kilogram Celsius degree. So if I do this math, I go 5e to the 6 divided by left parenthesis 30 times 450 close parenthesis. That gives me a change in temperature delta T equals 370 Celsius degree change. So delta T for iron is equal to 370 Celsius degrees. So I'll circle that way. Now I'm going to do water. And delta T for that is going to be Q over MC again. So I've got 5.000 times 10 to the 6 joules divided by 30.0 kilograms times 4,186 joules per kilogram Celsius degree. So this would be 5e to the 6 divided by left parenthesis 30 times 4186 close parenthesis. And this gives me a very small temperature change of 39.8 Celsius degrees, so that we have delta T for H2O is equal to 39.8 Celsius degree change. So you see, that made quite a difference. In fact, you could say 39.8, let's say 370 divided by 39.8 is 9.29 times bigger. But you also notice that 4,186 divided by 450 is about 9.38. Actually, it's 9.30. So pretty close to the same. That's exactly why it did that. Anybody have any questions on that? Okay, so that gets us to understanding how specific heat works. You can obviously tell the larger the specific heat, the larger the amount of energy required for a given temperature change. That's something that's important. Your book goes over a conceptual example, 19.3. It says a very hot frying pan. You accidentally make a bad mistake by letting an empty iron frying pan get very hot on the stove, 200 degrees Celsius or even more. What happens when you dunk it into a few inches of cool water in the bottom of the sink? Will the final temperature be midway between the initial temperatures of the water in the pan? Will the water start boiling? Assume the mass of water is roughly the same as the mass of the frying pan. Can anybody tell me what you think about that? I'm suspecting that y'all don't have your book open, so you know your answer will be one that's okay. It's one that you made up. Anybody have any ideas? Do you think the temperature will be midway between the 200 degrees Celsius that the pan was and say the 20 degrees Celsius that the water was? So halfway between those would be what, 180, it'd be 90 plus 20 would be 110. Does that sound reasonable or does it not sound reasonable? Would you think it'd be the final temperature of the two would be higher than 110 or would it be lower than 110? Anyone?
I would guess about halfway, just from my experience, like whenever I've been cooking and I put a pot in hot water, it seems to heat the water warm, but not like boiling.
Right, and actually, what you argued there sounds even more correct than dead center. But yeah, most people do think it would be about dead center, especially since they told us that the masses were about the same. Now, what you probably experienced was the water mass was quite a bit larger than the actual pan's mass, which is why it's not so easy to argue from. But in fact, if it was an equal amount of water and an equal amount of iron, what you'd find is it'd be much more likely to be, let's say, since the water was 20 and the pan was 200, it wouldn't be unreasonable to find that when it's all done, the water might have gotten up to 28 degrees Celsius. So that's the actual correct answer. I'm not saying exactly 28, but it's closer to the bottom side than it is to the middle. And that's because the specific heat of iron is 450, whereas the specific heat of water is 4,186. So it's a factor of almost 10 times larger, definitely a full 9 times larger. So you'd expect the temperature change to be 9 times as large for the iron as it is for the water. Does that make sense? So don't feel bad at all about getting that wrong. That's certainly the norm. And I would bet you out of 24 students that I have in a given lab day, when I ask them the same question, they probably out of 24, 22 of them would say halfway between, and 1 or 2 of them would say closer to the low temperature of the water. But one usually will say the other way around, just because we don't think of water that way. But yeah, water is an excellent, excellent insulator. The water won't start boiling, by the way. It turns out that there's an extra boost of energy that you need to make a water go from really hot at 100 degrees Celsius to boiling. That heat is called the latent heat. Now it's actually, that's the name we use interchangeably for the heat that you remove from it to make it go from a gas to a liquid. And we also use the same phrase for the heat that is gained by it when it goes from a liquid to a gas. So latent means like sort of sitting there inactive or whatever. So that's more of what happens when you actually cause it to cool. Is it stores a certain amount of energy, but that's what's going to happen next. So it turns out when you're trying to heat, let's say trying to heat water up from ice all the way to steam, what's going to happen is you have ice at, let's say, negative 10 degrees Celsius. And if you did that, let me give you an example of what's going to happen here. And your book actually has a really good diagram for this. What I will remind you is that our specific heats for ice and water are quite different. In fact, I'll say, whoa, didn't mean to do that. I'm going to say that C for ice is on the order of 0.5, and that's calories per gram Celsius degree. C for water and I'll put an L on it to mean liquid, is 1.00 calories per gram Celsius degree, and C for steam is equal to, let's say, about 0.48 calories per gram Celsius degree. Okay. So that's what water looks like at various phases. So what happens is, if you want to make a plot of, let's say, temperature in degrees Celsius versus heat in calories, and actually I should probably do this. Okay, you can start off down here at, let's say, negative 10 degrees Celsius. Okay, you have ice there. And what's going to happen is the ice is going to warm up, warm up, warm up, warm up. And we're going to say this is for, let's say, 100 grams of water as ice. That's what we're starting with. Okay. So once I add, in this case, 100 times 0.5, I'm up to 50 calories. Okay. Then what happens is the temperature of the water will remain exactly the same at 0 degrees Celsius in the ice state until every molecule has been broken loose from the lattice. The temperature will remain that 50 degree, or excuse me, that 0 degrees for an extended period of time until I add enough heat to let it go. Well, it turns out that latent heat in this case is called the heat of fusion. And this would be for water, for instance, it's about 79.7. Yes. And that's in going from freezing to not. So if we take and add 50 plus 79.7 times, now 79.7 is actually the kilocalories per kilogram or the calories per gram. So I'm going to have to add, since I have 100 grams, I'm going to have to add 7,970 calories to that. So in this case, it's about 8,020. So this will continue going until, and I'm going to make a line here because I don't have enough space. And that's going to be about 820 or 8,020 calories. At that point, it's now finally water. Okay. And now you can start adding heat again. And this time it's going to start raising until it gets to 100 degrees Celsius, at which point it's going to come to a stop and hold at a fixed temperature again. Okay. Actually, I don't like this being 100 grams. I can make these numbers prettier if I don't. So what I'm going to do is I'm going to take this and I mark it through that, and I'm going to say it's 1 gram. Then 1 gram going from negative 10 to 0 would be 10 times 50. Okay, so that'd be just 5. So that makes that a little better. I'm going to go here and erase this. Whoa, Nelly. And this is going to be 5.0 calories. And now this, since I've reduced it down to 1 gram at, oops, darn it, it really makes me angry. I can't tell you how angry that makes me. Okay, so I've got this here, that there. Okay. Now I'm going to take 5 and add it to 79.7 is equal to 84.7 because this distance right here is 79.7 calories. Okay. Now I've got 1 gram of water, and that's going from 0 to 100. So in fact, this amount right here is going to require 100 calories. So this would be 184.7 calories there. And what that tells you is that this span is 100 calories from here to here. Now, if I look up the heat of vaporization for water, I find that that's 539. So in this case, again, I've got to draw a little break because I just don't have the room to make it to scale. But ultimately, what I'm going to find is right here is this is 184.7. And I'm going to add to that 539. That's going to give me 723.7. And what we can see here is this is 539 calories, which is the heat of vaporization. So we call this L sub V, and we call this one, that's the heat of fusion. So we call that L sub F. Okay. At that point, then all of the water can change to actually be steam in the gaseous state, and it starts to climb up that way. And in fact, it can go, say, basically at a rate of 0.48 Celsius degrees, or actually, I should say 0.48 calories per Celsius degree. So that's really what that slope is. So that's what happens with all substances. Basically, you apply heat to them to heat them up, change their temperature, change their temperature, change their temperature, up until they get to the critical point, which would be like the melting point. So at that point, the water is going to stay at 0 degrees Celsius until all of the water is melted, at which time it becomes liquid water instead of gaseous water. But it's actually tend to have absorbed 79.7 calories. And then you can heat it up some more and bring it from 0 degrees Celsius up to 100 degrees Celsius, which is the next critical point. The amount of heat it takes there isn't that relevant. It's not a heat of fusion or a heat of vaporization, but it's going to lock it in at 100 degrees Celsius, and the water that's boiling will stay 100 degrees Celsius, assuming the pressure is 1 atmosphere, until an additional 539 calories have been added, at which time all of the molecular bonds between one molecule and another have been broken, and it can then have the actual atoms or molecules run off in a random fashion as a gas. So does anybody have any questions on that? All right, so what I just did there was bringing us up through the heat of vaporization.
You're muted.
We can't hear you.
Can you hear me now?
Yes.
Cool. All right. Was I muted the whole time I was explaining all that, or did that just happen a second ago?
No, when
It
you
just
just came back in.
Okay, good. Sorry, that scared me for a second. All right, so I skipped a little ahead a little bit just to talk about vaporization and that sort of stuff. There's a table for it too, table 19.2. So you'll be referring to that in your book, or we'll have to give you values on particular tests. But the main thing is what I want to go back to now is talk a little bit about calorimetry, because calorimetry is, what we use to actually determine specific heat of certain substances. So one of the experiments we do in our class is specific heat. And what we'll do is we try to get a solid object. We have a copper one, we have a tin one, we have a zinc one, and I think we have a brass one and maybe one other substance. But the problem with that, if you have a copper or a zinc or a lead or a tin chunk of metal, it's not easy to figure out the temperature of that metal. Does anybody have any idea how you might figure out the temperature of a solid metal? Can anybody think of anything? It doesn't have a little booty hole, so you can do it like a baby or something. So you can't just stick a thermometer in it, right? So what you can do in principle is you can aim an infrared camera at it, and the infrared camera will tell you the temperature of the surface. But in principle, the surface doesn't necessarily have the same temperature as the core. So it is quite a challenge to figure out the temperature of a solid body. So one of the ways you can do it is we can use the fact that I just covered, which is that when you take water and bring it up to 100 degrees Celsius, that water will stay at 100 degrees Celsius until all of the water boils away. So if you put a hunk of metal in a container of water that's boiling, and you leave it there for a couple minutes, since the metal is actually a conductor, it takes very little time to reach equilibrium with the water. But take a couple minutes and be safe. If you do that, then you can be certain that when you pull that metal out of the water, it will have exactly the temperature of the boiling water, and generally that's right at 100 degrees Celsius. If the atmospheric pressure is quite low, it might be a little bit lower. If the atmospheric pressure is quite high, it might be a little bit higher. But in general, it's almost always 100 degrees Celsius. And you can even test it with a thermometer that goes up to 100 degrees Celsius, of course. You can test the water. And then if you left the metal in there long enough, which again, I can't imagine more than really, to be honest with you, I doubt it's even a whole minute, but we normally leave it in 5 minutes. When you do that, then you can be assured that the temperature of the metal is 100 degrees Celsius. Then all you have to do is put it in something that has a known specific heat and see how the temperature changes. The way we do that is we often have a jar like that, and this jar, in fact, is made of aluminum, because aluminum is a good metal that doesn't corrode very easily, doesn't corrode very much, very easily anyways. And
If you're writing something on the iPad, you can't see it.
yeah, thank you for reminding me. I was just realizing that when I remembered that the camera had left me. So thank you for that. Yeah, I will do that on occasion too. So by all means, let me know. So I'm drawing a aluminum container right now. You're going to see it pop up in a second. And this aluminum container is sort of the outer walls of like a thermos or something. Okay. Now, in addition to having that, what we're going to have is inside of here, there's going to be a little ledge like this. Okay. Now, actually, the ledge isn't just internal. You'd see it on the outside too. It's actually around there. But the main thing is, I'm trying to get you some idea that we have a mechanism to separate the canister inside from touching this part right here, which is basically a non-conductive wafer with a hole in the middle. Okay. It's in fact generally made out of cardboard. Okay. So by laying that there, I can then suspend another aluminum cup in that hole of that wafer, and it can't touch the outer aluminum container. So now what I'm going to do is draw yet another container. And that container is going to be like that. This guy, dang it, here, this guy is aluminum. And this guy is aluminum. And then inside of here is water. Now we have a lid and stuff we can put on it, but generally speaking, you don't lose too terribly much heat through the top. You do lose some, but we haven't ever found it to be problematic without a lid. And it's a lot easier to do without a lid. So that's why we go with it this way. But what we do is we fill that up with water to some extent, but really we just want enough water for it to completely cover the metal that we put in there. So I'm going to now choose a different color for the metal, and we'll say the metal looks like this. Okay. And that metal, let's say, is copper. Okay. So by making a calorimeter like this, and this is what this is a calorimeter. By making a calorimeter like this, what we've done is created a little wafer of air, a layer of air all around the outside of the inner aluminum cup. And the only way heat can be conducted from that outer aluminum cup to that inner aluminum cup is through that purple cardboard wafer. Okay, so it's only touching in this very thin little area right here, mainly meaning the thickness of the little cardboard slab. That's not a very much conductive area. As we'll learn at the end of the chapter, the amount of heat that can flow across a surface like that is directly proportional to the surface area. Well, that itty bitty thin area all around the side is itty bitty thin. So that's going to be not conductive to heat moving through it from either the aluminum cup outside to the inner aluminum cup or from the inner aluminum cup to the outside. It's not going to be very conductive. Not only that, the size of the wafer from the inside touching the cup to the outside touching the cup, that's kind of big. So that's prohibitive as well. And then thirdly, it's made of cardboard. So it's not a good conductor. It's a very good insulator. So that's another reason. And since it caps off, it keeps the air from circulating around that inner cup so we can get rid of convection and stuff like that. That leaves really the only mechanism by which heat could flow is by radiation into that. So we have in there, of course, a thermometer. And what we do is we drop the 100-degree copper into the water. And just before we did that, we read the temperature of the water. And we already recorded the mass of the water, and we already recorded the mass of the inner cup. And we put the 100-degree Celsius copper sample in the water, and we know its mass as well. That hot metal will tend to raise the temperature of the water inside the cup. And let's say it started off at 20 degrees Celsius. It's not uncommon for it starting off at 20 degrees Celsius, and then the water temperature will reach a max as you're stirring it with that thermometer and everything, trying to make sure the water is distributing uniformly and taking all the heat away. You'll see the thermometer go up, 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 and it usually reaches around 23.6. So it'll go from 20.0 degrees Celsius to about 22.8 or 23.1 degrees Celsius, something like that. Not a very big one. Okay. Even though the metal was much hotter, and we find out that the metal will normally be, let's say, mass of the copper will be on the order of 58 grams, and the mass of the water, will be on the order of 120 grams, something like that. Not hugely big, but a little bit bigger. Okay. But that's the various outcomes you get. So that's what a calorimeter is, and that's what it does. So calorimetry is when you assume you have something like this where Q equals 0. So for a calorimeter, Q total is approximately equal to 0. Okay. So that means you can say Q total equals 0 is one equation that can be used. And that'll allow you to solve for the specific heat. I have found that that's not the easiest way to do it. My students, you're welcome to do it this way, by the way, and your book does both. It shows you both. The way I do it is I say Q hot equals Q cold. And what I mean by that is the hot thing's going to lose heat and the cold thing's going to gain heat. And you just keep track of which those are. And in this case, you make all the signs positive. So So you got to keep all the terms positive. So that delta T thing that I've been telling you about, in this case, you just take big temperature minus small temperature every time. You don't take, final minus initial. You just make sure it's always positive. I've found this works out a lot better. And then you just solve it accordingly. So as an example, let's actually solve the issue that we have. Let's find the specific heat of copper. So this is a made up data for determining C of copper. Okay, so what I want you to know is none of this is real. I'm just making up numbers, and we're going to do that. So what we know is the copper came in. T initial was 100.0 degrees Celsius. And for the water, T initial was 20.0 degrees Celsius. And T final for the aluminum equals T final for the water equals T final for the copper. All of those I'm going to say is 22.8 degrees Celsius, just because that's the one I chose. Okay. Again, completely making it up. So let me show you how to work out what the specific heat is. So the hot things I'm going to put on the left, the cold things I'm going to put on the right. So what I'm going to do is solution. I'm going to say the mass of the copper times specific heat of the copper times the temperature change of the copper. Now, this is where I've got to realize the copper is going from 100 degrees Celsius to a much lower temperature, and I need the term to be positive. So I'm going to say 100.0 degrees Celsius minus 22.8 degrees Celsius. Now that's the only thing that's losing heat. So I could call this Q hot, or I could call it Q lost and call this Q gained. Either one of those is fine. But that's the only thing that's losing heat. Now on the other side, I'm going to put the mass of the water times specific heat of the water. Now in this case, the water is going to go from 20.0 to 22.8. So I've got to do 22.8 degrees Celsius minus 20.0 degrees Celsius. And then I also got to take into account the aluminum cup, the inner aluminum cup. And that's going to be the mass of the aluminum times specific heat of aluminum times, in this case, it's going to be 22.8 minus 20.0 degrees Celsius again. And that's basically it. That's all the stuff. Now I just have to put in the numbers and solve it. And I got to use, you know, for instance, the specific heat of aluminum, because obviously I'll need that. And I think I have it right here. Yes. Okay. So now I can put all these numbers in. I'm going to use calories. I know the mass of the copper is 58.0 grams. The specific heat of copper is what we're solving for. This is going to be 100 minus 22.8. That gives me 77.2 Celsius degrees. And then the mass of the water, I said, was 120.0 grams. Again, these numbers are completely made up. The specific heat of water is 1 calorie per gram Celsius degree, and 22.8 minus 20 is 2.8 Celsius degrees. And then the mass of the aluminum cup, I said was, did I give a value for that? I thought I did. Mass of the aluminum cup, aluminum cup, aluminum cup. I didn't write it down anywhere. The mass of the aluminum cup's on the order of 60. So I'm going to say aluminum cup. So I'm just going to call that 60 grams like we do it all the time. So that's 60.0 grams times specific heat of aluminum, which is 0.22. And that's calories per gram Celsius degree, and then 2.8 Celsius degree again. So I can do all this calculation pretty easily. I'm going to do 120 times 1 times 2.8. That's going to give me 336. That's 3 sig figs, which is what I expect. And that answer comes out in calories. And then I can do 60 times 0.22 times 2.8. And that's going to give me 36.96. And that's 1 extra sig fig, but that's in calories as well. And then I'm going to go 58 times 77.2. That gives me 447.6. Now that should only have 3 sig figs, so these two guys are not sig figs, and that's times Cu copper, and this is grams Celsius degrees. Okay, so the specific heat of copper would be 336 plus 36.96 gives me 372.96. Now, in this case, neither one of these two are sig figs. And now I've got to divide all this by 4477.6 grams Celsius degrees. And these two numbers aren't sig figs. So I'm going to divide this by 4477.6. And that should give me 3 sig figs, and I get 0.083. And notice the units work out to be calories per gram Celsius degree. So that's a typical calorimetry problem. Anybody have any questions on that? So notice how we used the thing that was losing heat, I put it on one side, and all the things that are gaining heat, I put on the other side, and then I made sure each term was positive. So that's the key thing you got to get out of all this is realize the terms have to be positive if you use that. So ensures positive terms. Ensures positive terms here. And ensures positive terms here. Okay. So that's good enough. Anybody have any questions on that? All right. So remember, you need to start planning. You do have a online test that's due next week. I'm leaning towards it being due Wednesday night, and I'm hoping that we'll have the face-to-face test on Thursday evening with your lab instructor. I'm going to make sure that's okay with Miss Raskovic. And when you're actually doing the work to prepare for your online test, in this case, you're still doing the same thing in preparing for the face-to-face test because they're both going to be on chapters 1 and 2. So I will leave the practice test. It'll be open until the time you're supposed to start your exam, which I think, doesn't your class start at 8:15, your lab class? Does that sound right to you guys?
2:15.
Oh, okay, gotcha. So, 2:15 is in the afternoon before. Okay. So, thank you. I appreciate that. I completely forgot. She didn't tell me that. So at 2:15, that practice test will disappear, and then you can go and take the online, or excuse me, the face-to-face test. But make sure you finish the online test beforehand because you don't want to get a 0 for that. That's supposed to be just an easy test. You're allowed at least 3 attempts. That's normally what I give you. And I only take your highest. You are allowed open book. You're allowed open notes. You're allowed to do Google searches. And as I said, I used to take a lot of pains to make sure you had a limited amount of time. And I tried to, sort of skirted along such that you only had enough time to maybe look up one problem. I'm going to leave it up to you to be responsible for your own education by saying if you find that you're consistently having to look up more than one question, even every other trial of the practice test, you're probably not ready for it. If you have to look up more than one question every 2 or 3 practice tests, you probably need to do a lot more practice tests. Similarly, when you actually take the online test, if you have to look up more than one question, I would say you're not really learning sufficiently to take that yet, but you're going to be able to look up more so you can still get 100. That's fine. And I don't mind you getting that good grade. I want you to get those good grades. I just want you to know that you're not doing as much in terms of learning that you should do. There might be a little too much leaning on looking up answers. There might be a little too much leaning on getting ideas of how to solve problems from looking at Chegg, all of which are completely legal on the online test. I just want you to be mindful of that and take responsibility for you knowing that, hey, if you want to be an engineer or a scientist, this is sort of the bare minimum of science that you have to go into that. So if there's some part of it you're not learning, it could come back and bite you very severely later. So that being said, everybody is free to go. Please feel free to contact me if you have any questions. Remember, email me if I don't get back to you within one school day. You can go ahead and send me a text message. Just remember to include your first and last name and what class you're in. And have a good, safe weekend. And thank you for coming, everybody. This will be posted by tomorrow morning, by the way, but it'll probably be posted.
I had a question about, well, it's like an email question. I don't know if I've been emailing you at the right email.
Okay.
just because I've emailed you a few times and I never got a response back.
Okay, that could be me being a slacker because I've had a lot of things going on right now. I've got a lot of different stuff, but let me put my email here for you, so I don't have to say it out loud and then get a bunch of stuff. But I just typed it into the chat. That is my email. If you send it to me and you put the subject line starting with our course number, like it says in the syllabus, and you use your TCC email, I should have got it. And if I didn't answer it, it's because I'm a loser. Okay. But if you've been using that, then everything's fine. It's just me being a loser, and I apologize for that. That's when you want to go ahead and send me a text message. And I'm going to put my phone number here again, even though it's in the
But
syllabus.
I had texted you too, and then I never got a response.
Oh,
That's why I was just wondering.
okay. Let me see that one then. I've been responding to my text messages. Let me see. No, I don't have.
Is that the same phone number in the syllabus?
That should be it. Let me look at it again. Yeah, that's the right phone number. That should be the one in the syllabus. I don't see any. I did get one from someone. No, that was a different student. Yes, I got yours. I see that somehow it got down to the bottom of my page and I didn't reply to it, but I'm reading it right now. Okay, so far as making up the labs go, you can talk to Miss Raskovic about that. If she doesn't have a way, I have a way, and I can adjust your grade after the fact. She might not be willing to do it, and that's her prerogative. She gets paid an abysmally small amount of money for doing what she's doing, and she's really good at teaching and really good at teaching our labs and our lectures. So I'm not trying to say anything bad about her, but if she can't let you make them up, then talk to me and I can adjust it, because what she's going to do at the end of the semester, she's going to turn in your grade to me, and that's going to reflect, for instance, maybe you missed two lab grades, so out of 11 or something like that. So what I can do is adjust that by 2 lab grades going from 0 to 100 or to whatever grade you make. So if you need,
Okay.
I can do it. Okay.
And also, has there been a test already? I wasn't sure.
No, there
For
hasn't.
a face test.
No, there hasn't. There is an online test that's available right now. And the reason why I made that available is because today, I think tomorrow is the last day you can drop and get some tuition back. So if you take that, your 3 times, you can get an idea of what the tests are going to be like, but that's not the same thing as a face-to-face test. But I did make the first face-to-face test early enough where you can drop the class just without a tuition refund. But I very, very rarely do I ever recommend someone drop my class. I will work with you. I will help you. We will get you passed, but it's going to take a little bit of work from you and from me if you have any problems. And I'm glad to do that for you. So I'm probably never going to recommend you guys to drop, but just know that will be an option after your first test, face-to-face test. Okay.
Professor Younger.
Yes. Go ahead, Jan.
Okay. I was wondering, are we allowed to have
And-
a note sheet for the first
and-
face test?
Face-to-face test, the only thing you're allowed to have is that equation sheet that is in our week or in our important course documents module.
Okay.
The one I just mentioned to you guys, it says 242 PHYSICS chapters 17 through 31 or something like that. That's the equation sheet you're allowed to have. I would recommend you print that out. It's a couple pages. Print that out and start using that when you're doing homework as well as when you're doing practice tests. And then, of course, you'll use it on your online test and you'll use it on your face-to-face test.
Okay. All right. Thank you.
No problem. Jonathan, do you have another question?
Oh, so
I'm going to stop recording in case you have to ask anything personal or grade wise or something like that. And I don't see any use of having.
oh, so was there